Hi, I'm Hossein and welcome to my YouTube channel. This video is the 5th episode in the Grasshopper tutorial series. If you remember, we previously had a short intensive course to cover the basics of Rhino. At the end of that course, we explored an architectural form together and saw how it could be modelled in Rhino using different methods. In this episode, we're going to take that same form and model it this time using an algorithmic approach inside Grasshopper. We'll see how the design logic can be implemented parametrically instead of modelling it manually. In the first 4 episodes of this series, we focused on the basic concepts of Grasshopper, from getting familiar with the interface to understanding data, lists, and the main components. Now, we've reached a point where we'll start taking a more project-based approach. By solving more practical examples, we can gain a deeper understanding of Grasshopper. In this video, I'll use as many of the same commands and components we've covered in the previous episodes as possible. Naturally, there are a few new components as well, and you'll learn how to use them right in the context of this project. It's natural that the first parts of any course, especially the basics, can feel a bit dry, but from here on, the course will get more engaging and give you a more hands-on experience with parametric design. Finally, I'll share the final file of this algorithm as a link in the description of this video, so you can work on it yourself and practice. All right, let's get started. Before we dive into writing the algorithm, let's do a quick overview to see exactly what we're going to do and the general logic behind it. First, we have a base rectangle, which we'll use as our initial form. From this rectangle, we create an offset to generate a secondary boundary for controlling the form. Next, we have another rectangle that we'll trim using the first rectangle. The goal here is to remove the extra parts and end up with a clean, controlled line. After trimming, the result is still just a few line segments. Here, we convert these lines into a clean closed curve so that we can use it as a section. This step is crucial because the quality of our final surface depends directly on how clean these sections are. Next, we adjust 4 different sections, making sure their order and orientation are correct for surface creation. Essentially, we're setting up the sections so Grasshopper can connect them properly. Once the sections are ready, we loft them together to create the main architectural surface. This is the first moment where we can see the algorithm's result as a tangible 3D form. In the last step, we apply contours to the surface to get regular cut or contour lines. Finally, we extrude these contours to achieve the final volume. Now that we know exactly what steps we'll take, and the general logic of the algorithm, let's start writing the algorithm in Grasshopper and implement this process step by step. First, I create a construct point and use this point as our starting reference. For now, it just serves as a reference and will be the basis for building our initial geometry. Next, I add a rectangle. I place the rectangle on the XZ plane so that the form is created on this plane. I set the X size to 1000 and the Y size to 500, giving us a rectangle with specific dimensions on the XZ plane, which forms the base geometry of our algorithm. After that, I move on to the offset curve. To control the offset amount, I create a slider and set it to 20 centimeters. I activate the negative option, so the offset goes inward. Then, I connect the rectangle output to the curve input C of the offset curve, and the slider to the distance input D. This gives us an offset rectangle that we'll use in the next steps of the algorithm. The negative component in Grasshopper is used to get the negative of a number, or a set of numbers. The logic is simple. It takes any input number and reverses its sign. So if the input is positive, the output becomes negative, and vice versa. This component is useful when you want to reverse a direction, move something in the opposite way, or invert numeric values, for example, reversing a vector, or changing the coordinates to move an object along the opposite axis. In this step, I connect both the main rectangle and its offset to the curve input by holding down the Shift key so they enter this stage of the algorithm at the same time. Once the connections are made, I hide all the geometry we no longer need except for the final curve to keep the workspace clean and make it easier to focus on the next steps. Next, I move on to point on curve. Here, I connect the original rectangle to the curve input of the point on curve component, so we can extract points along this curve to use in the following steps of the algorithm. The point on curve component in Grasshopper is used to place a precise point on a curve. It works by taking a curve as input, along with a parameter value t, usually between 0 and 1, or based on the curve's length. The component then outputs the point corresponding to that parameter on the curve. This is useful for precisely locating points along a curve, dividing a curve into specific points, or creating relationships between other geometry and the curve. In other words, by changing the t value, you can move the point continuously along the entire length of the curve. Next, I create another rectangle, but this time I place its center on the point we got from the point on curve component. I set the rectangle's plane again on the XZ plane. I choose the rectangle's length based on the opening size we need, and set the Y value to 30. This number is just for control thickness. It only needs to be slightly larger than the wall thickness. Here, I chose 30. After creating the rectangle, I use the move component to shift it along the negative Z direction. Initially, I use the same 30 value, but for better control, I set the final move distance to 40 and divide it by 1.5, making the movement smoother and more precise. Finally, to subtract this rectangle from the main form, I use trim with region so that the extra parts are removed, preparing us for the next steps of trimming and creating the section. The trim with region component in Grasshopper is used to trim geometry using a closed region. It works by taking one or more geometries, like curves or surfaces, and trimming the parts that lie inside or outside the specified region. In other words, the region acts like a pair of scissors, keeping or removing only the parts of the geometry that intersect with it. This component is useful for refining shapes, creating custom cuts on surfaces or curves, and isolating specific parts from complex geometry. In this step, I connect the curve we created in the first step to the C input, and the rectangle we just set up for the opening to the R input. After that, I convert the outputs to curves so we can clearly see the result of the trim and the exact lines that are generated. From these outputs, I select the one we need, called CO, because it's the clean, closed curve that we'll use as our section. Now moving on to loft, I connect the CO output to the loft component, but since the data comes in a tree structure, I first flatten the tree to make sure the loft is created correctly. I connect the loft output to a curve, and then hide all the geometry except the final curve to keep the output clean and clear. At this point, we have our first required section, a fully parametric section, where all parts can be easily adjusted and controlled. Now, I take a copy of the section we just created, so we can use it as a base for setting up the next section. Finally, I tidy up the script a bit and group the entire part related to the first section to make the definition cleaner and easier to read, which will help us work more smoothly in the next steps. At this point, I'd like to sincerely thank all of you for your support, your feedback, and your comments, and for helping this channel grow and continue through your encouragement. If you find this video useful, liking and subscribing helps this content reach more people. Thank you for your attention and support. Now let's continue with the tutorial. Alright, now let's move on to the next section. I take the final curve from the previous section and use the move component along the y-axis. For now, I set the move distance to roughly 780 units from the base point. This value is approximate, and we can refine it later if needed. Now, let's move on to the next section. As before, I take a copy of the section we have, but this time I want the form to rotate slightly from the halfway point onward. To do this, I apply a rotate on the final curve. I connect the moved curve to the G input of the rotate component. To define the rotation center, I use the area component. I take the area input from the first base rectangle of the algorithm, connect the output of the area's center to an XZ plane, and then feed it into the P input of rotate so that the rotation axis is correctly defined. At this stage, I also slightly increase the move distance of this section to position it correctly relative to the previous section. Next, I right-click the rotate component and activate degrees so the rotation angle is set in degrees. I connect a value of 90 degrees to the A input as a negative number, which rotates the curve 90 degrees. And just like that, our third section is created. Now, let's move on to the fourth section. I follow the same process as before for the final section, but this time, I increase the move distance from the starting point so that the last section is positioned exactly where it should be. At this stage, I tidy up the entire script again and group each section separately to make the definition cleaner and easier to read. Now, it's time for loft. I add the loft component and, while holding the Shift key, connect all four sections to its input to create the initial surface. Then, by right-clicking the output O and going to Loft Options, I adjust the loft settings, set the mode to loose, and apply the changes. Next, we move on to contour. I add the contour component, connect the loft output to the S input, and use the initial point we created at the very beginning with construct point for the P input. At this stage, it doesn't matter which section you use as the base. For the direction, I define a vector along the y-axis and set the distance d to 30 centimeters. Now, I extrude the contours we just generated. I add the extrude component, and for the direction D, I use the same y-axis vector with the same 30 centimeter distance we used for the contours. In the final step, I use cap holes to close any open surfaces so that the final volume is complete. The cap holes component in Grasshopper is used to fill holes or openings on a surface or a brep. The logic is simple. If a surface or 3D volume has open edges, like a box without a top, this component identifies the open edges and creates a new surface to close them. Its main use is when you want to prepare geometry for 3D printing, volume calculations, or Boolean operations, because most solid operations require a fully closed geometry. And that's it. From here on, by changing any of the parameters at any stage of the algorithm, you can update and modify the entire form we modeled in real time. In this video, we saw how to build an architectural form step by step, using an algorithmic approach in Grasshopper, from defining the base geometry and sections, to lofting, contouring, and finally creating the complete volume. The key point of this project is that almost all parts of the form are fully parametric. By simply changing a few numbers, we can get completely different outputs, which is exactly what shows the real power of Grasshopper. If you found this video helpful, liking it will help the tutorial reach more people. And if you want to continue this journey with more real-world examples and projects, make sure to subscribe to the channel. I'd also be happy to read your thoughts, questions, or suggestions in the comments so we can cover them in future videos. Thank you for supporting this channel and for taking the time to learn. See you in the next video, and until then, stay creative.